All right, welcome back. Let's look at another example that relates this concept of an accumulation function with those concepts from yesteryear of increasing and decreasing and extrema and concave up and concave down and all that business. So in the previous example, we did that, but we had the function to work with. Here we have a graph to work with, but I think we can follow a lot of the same techniques, but we just are going to solve from a graphical perspective this time. So let's see. We have this function h, which is the accumulation function, the area accumulation function of f of t dt, where f of t is given right here. So let's be clear what we're given. This is the graph of f of t. The graph of h is accumulating the area. So just to keep in mind, this is not the graph of h that we're looking at. The graph of h, I'll actually graph it here in the very end to confirm all our answers with using Desmos. But think about it just, briefly. We start off at -10, and we start off accumulating area, but negative because it's a definite integral and the region's below the x-axis. So we start off, we're accumulating negative, and so we have a function that's decreasing starting off, and then eventually you get to -2 and you start adding positive area. So instead of accumulating negative area like we were from -10 to -2, we start accumulating positive area. So at -2 we turn around and start increasing. And so then we kind of do that back and forth until we get to +10. But the graph of h will be the area calculations accumulated. Basically, if you evaluated this integral like an infinite number of times between -10 and +10, plot all those values, and then connect the dots, you get the graph of h. But this that we're staring at right now on the screen, that is the graph of f, not h. So let's see here. If we want to figure out where the function is increasing or decreasing, that means we need to find the derivative. Okay, and this is where our new techniques come into play, because we know the derivative of h is what? H prime is given to us exactly by the application of the fundamental theorem of calculus part 1. Because that calculus theorem says if we have the derivative of an accumulation function that looks identical to that, we know that the derivative is what? It's the integrand f of t evaluated at x. So equals f of x. In other words, we have the derivative right in front of us. We're staring at the derivative. That is the graph of the derivative. The derivative of h prime, is looking at us. So we could say this is equal to h prime, the graph that we're looking at. Now, how can we use that to figure out where the function's increasing or decreasing? Okay, well, remember, a function is increasing. This was we had a definition a while back that said you're increasing corresponds to here. Actually, let me phrase this a little better. We said that a function will say h. H is increasing when h prime is greater than 0. So if this is the graph of h prime, where is it greater than 0? And then we can also ask ourselves the question, to find where it's decreasing, we know that h is decreasing where, I got away from me, where h prime, the derivative, is less than 0. And by less than 0 and greater than 0, we literally mean the graph is below the x-axis, less than 0, above the x-axis, greater than 0. So we can just read off the portions where the graph is above or below the x-axis. So let's do decreasing first. The graph is below the x-axis right there where that semicircle is below the x-axis, and then below the x-axis over that domain. Okay, again, I'm looking at the graph here. This is the graph of the derivative. So it's below the x-axis where I just highlighted yellow. So that tells me that the function h is decreasing on let's write our answer down here. So let's see. Answer to A. H is decreasing on those intervals I just highlighted. So that's -10 to -2, union 2 to 6. Now, what about our definition for increasing? A function is increasing where its derivative is above the x-axis. So where is the derivative, the graph at which we're staring at right now, where is it above the x-axis? Well, it's above the x-axis between -2 and +2, and between 6 and 10. So those are the intervals where h is increasing. Increasing on, what was that? -2 to +2, union, and then we have 6 to 10. So there we go. Easy peasy. There's where the graph, that's where the graph of h, which by the way right now is unknown, the graph of h is increasing and decreasing on those intervals. Check mark. Now, how can we figure out about relative extrema? Remember, we have the first derivative test, where a graph changes from increasing to decreasing at a critical value. Well, then that's a relative max. Where the graph changes from decreasing to increasing at a critical value, well, that's a local minimum. So if we know where the graph changes from increasing to decreasing, we can identify the local extrema. So let's see, local minima and local maxima. Where does the graph, let's go from left to right. At left to right, notice we change at -2 from decreasing to increasing. That means that -2 comma something is a what? A local minimum, because we're changing, again, yellow is what I used for decreasing. We change from decreasing to blue, increasing. Decreasing to increasing necessitates the fact that we have a local minimum. What about at +2? At +2, we change from the graph being above the x-axis, and this is the graph of the derivative, so the derivative changes from positive to being below the x-axis negative, and so that's going to give us a local max. So at +2 comma something, we have a local max. And then what happens at 6? At 6, we were below the x-axis again, and we changed to above the x-axis. In other words, our derivative changes from negative to positive, so that's another local minimum. So that would be 6 comma something is a local minimum. So we have 3 relative extrema, 3 local extrema. Now I suppose we should go find the y values. Now how do we do that? Well, okay. We have to do that by going back to our accumulation function. So let's see here. Let's erase that. And let's say we want to evaluate, because we always say go back to the original function to find your y values. In other words, h. Well, we need to find h of, let's go in order here, h of -2. Well, what's h of -2? That's the definite integral from -10 to -2. Replace the x's with the -2 of f of t dt. So it's the accumulation function value between -2 and from between -10 and -2. Well, let's think about it. Let's look at our graph. What is that? It's this region right here between -10 and -2. And what do we notice? That's a what? That's a semicircle. Now do note the semicircle is entirely below the x-axis, but how do you find the area of a semicircle? So you find the area of the circle first. So what's the radius there? Between, it's what, -6 and 10. Sorry, I covered it up. But the center's at -6. So between -6 and -10, that's a radius of 4. So r equals 4. So the radius is 4, which means the area of the circle would be pi times 4 squared, so 16 pi. That's the area of the circle. The area of a semicircle would be half of that, 8 pi. But remember, that is entirely below the x-axis. So we say the area is 8 pi of the semicircle. But the definite integral, the signed area, the net area, is negative 8 pi. So the y value is negative 8 pi. So the y value of negative 2 on our local min has a y value of negative 8 pi. Okay, cool. What about the y value of positive 2? Okay, so we keep accumulating area. So we need to evaluate h of positive 2. This is the definite integral from negative 10 to positive 2 of f of t dt. Okay, so we've already got half the answer there. So we have this region right there, which I know has a definite integral of negative 8 pi, but then we keep marching along the x-axis until we get to positive 2. But notice, we have this shape now to consider. Now think about it though, that's a triangle. It's entirely above the x-axis. So it's going to have a positive contribution to the net area, the accumulation function. So I'm going to have what? I'm going to have the original negative 8 pi. That's the red because I'm going from, again, negative 10 all the way to positive 2. So I have negative 8 pi, but then what's the area of that rectangle? Sorry, that's a triangle. What's the area of the triangle? Well, okay, it goes from negative to the basis from negative 2 to positive 2. So that's a base of 4. And it goes, the height right there is 5. So let's height 5, base of 4. 4 times 5 is 20, divided by 2 is 10. So negative 8 pi plus 10. So the y value of that was my local max, is negative 8 pi plus 10. Need a little more room there. Let's see, negative 8 pi plus 10, like so. Okay, now what about 6? I need to get the y value of 6. So h of 6. So that's the definite integral from negative 10 to 6. Again, I'm going back to my original definition of h. I'm plugging in the 6. So that's the accumulation function from negative 6 to 10, f of t dt. Okay, watch what happens here. Cool. So now I have the original, or let me write that down. The original negative 8 pi, that's the semicircle below the x-axis. Then I have that plus 10 is the blue triangle. But now what happens if I keep accumulating area from 2 to 6? I'm below the x-axis again. And it appears to me that that's an identical triangle, right? The base here is at negative 5, so the height is 5. It goes between 2 and 6, so the base is 4. So we have an area of 10. But that triangle is entirely below the x-axis, so we have 10 plus negative 10. So we have to count it in a negative fashion. And so that cancels out the triangle that's above the x-axis, and I get negative 8 pi again. Okay, so I get the same exact y value for both of my local minima. I get a y value, again, of negative 8 pi. All right, cool. That's our local extremas. We've found our intervals of increase and decrease. We found our local extrema. Now let's rinse and repeat, except now we need to talk about the second derivative because we want to talk about concavity. And concavity requires us to talk about the second derivative. Okay, so let's see. How can we get the second derivative? Okay, let's think about this. So h prime is what we're staring at. Here, I'll erase the shading. We're staring at the graph of h prime. F of x is the graph of h prime. So what would h double prime be? Okay, so up here, I know that h prime equals f of x. So if h prime equals f of x, that implies that h double prime equals what? The second, if I think about taking the derivative of both sides of that equation, the derivative of both sides gives me h double prime equals f prime. If I take the derivative of the left and right, you get h double prime on the left, f prime single prime on the right. Now, how does the graph help me out in this respect? Think about it. If this is the graph of f, then the derivative is when I need to consider the slopes of f. So if I need to figure out, in other words, if I need to figure out where the second derivative of h is positive or negative, then I can figure out where the slope of f, i.e. the derivative, the slope, is positive or negative, because I can observe where the graph is either increasing or decreasing. Okay, let me summarize some known facts. Okay, so h is concave up where h double prime of x is greater than 0, and h is concave down where h double prime of x is less than 0. Now, the known fact is this: h double prime is equal to f prime. That is, the slope of the given function. So if I look at that function, and I can say, where is the slope negative and where is it positive? In other words, where is that function falling from left to right and where is it rising from left to right? That's telling me where h double prime is positive or negative, because h double prime equals f prime, according to what we know about the fundamental theorem of calculus part 1, and then taking the second derivative. Okay, so if I go over here, and now we have part C, let's see, we're going to have h is concave up on what? And h is concave down on something also. Now let's get a highlighter. Okay, now what we're looking for is where the derivative, i.e. where the slope, because slope is derivative, where the slope of this function is negative. That's where the graph is concave down. So where is it negative? Well, the graph is falling from left to right to start with, and it's falling until you get to -6, right? Because at -6, that semicircle starts rising again. So we could say the graph of the derivative, the slope of this graph, which is the second derivative of h, is negative whenever we're between -10 and -6. Where else is the graph falling from left to right? Where else does it have a negative slope? Well, starting at the origin, it's falling from left to right and falls until you get to 4, right? Until you hit that little valley down there. It's falling from this little peak to that little valley. So between 0 and 4, it's falling. And I think that's the only places it's falling. What about where the graph is rising from left to right? Notice that starting at -6, like this, the vertex of this semicircle, it's rising until you get to what? Well, it's rising until you get to -2, then keeps on rising until you get to 0. So the graph is rising from -6 to 0. And then notice this little valley down here, this little trough, it's rising until you get to what? 8. So from 4 to 8, the graph is rising. Now, the slope is 0 from 8 to 10. In other words, the slope is constant. That tells us the second derivative is constant. Okay, we'll have to talk about that when we get there, but we'll do that in just a second. Okay, basically a second derivative being constant means that the original function between 8 and 10 is linear, is what it means for there's no concavity. So I guess we'll need to add a little bullet point here. H has no concavity on 8 to 10, because a linear function has no concavity. A straight line In other words, it's not bending up or bending down. It's just a straight line. It's a linear function. Okay, so now the yellow is where we were concave down, where the slope was negative. And again, what we're doing here, this is the slope of the derivative f prime. So we're looking for f prime, which is the second derivative of h. H double prime equals f prime. Again, our important thing up here, important fact up there. So we're concave down on, that is -10 to -6. And then again, we're yellow, concave down, a derivative negative from 0 to 4. So union 0 to 4. Now we are concave up where I highlighted blue. So that is what? From that vertex of that parabola. So that's -6 to the origin, 0. Union 4 to 8. And again, there was no concavity from 8 to 10 because the function turns linear. All right, now that's the concavity behavior, so check mark. And now to answer question D, well, remember, inflection points occur when you have a continuous function that changes from concave up to concave down, or concave down to concave up. So basically, where does the function change from concave up to concave down? Because this is a continuous function. It's not discontinuous between -10 and +10. So anywhere it changes from concave up to concave down to concave up, or vice versa, we have an inflection point. So that's going to give us where our first change is at -6. We change from concave down to concave up. So that's going to be an inflection point. Then we change again at the origin is 0. At 0, we change from concave up to concave down. So at 0 comma something is an inflection point. And then again at 4, we change from concave down to concave up. So at 4 comma something, I'll have an inflection point. And now, okay, that last change went from concave up to no concavity. And you know, there's not an inflection point in that case. There's just, well, you'll see what happens in the graph. Okay, but there's no concavity. Okay, I'll show you the final graph here in a little bit. So let's find the y values. Then we have to find the y values doing the exact same thing we did to find the y values of the extrema. So we have to evaluate the original function h. So h of -6, that is the definite integral from -10 to -6 of f of t dt. Okay, so let's get out the shading again, and let's work with our accumulation function. Okay, notice that from -10 to -6, we're accumulating a quarter circle. It's below the x-axis. So we found that the entire semicircle below the x-axis had a net area of -8 pi. If you want a quarter circle instead of a semicircle, that's half. So it's half of a circle, in other words, and it's below the x-axis, so it has a net area of -4 pi. Okay, so our y value of that inflection point is -4 pi. Now what about h of 0? Here, let's get those out of the way. Give me a little more room. H of 0. Well, that's the definite integral from -10 to 0 of f of t dt. So we're accumulating area between -10 and 0. Now, graphically, let's do a little shading. So from -10, we accumulate that region, which is, we already know what the answer there is. And then we accumulate some positive net area between -2 and 0. So we get this, this right triangle, which is half of the isosceles triangle we worked with before. Okay, so what do we have? Well, we know that the semicircle has a net area of -8 pi. And then that entire isosceles triangle had an area of what? Of 10. So half of it will have an area of 5, right? And again, we can verify that the base is 2, height is 5, so 2 times 5, 10 divided by 2 is 5. So yeah. And by the way, it's above the x-axis, so we're going to count in a positive fashion. So the accumulated area from negative 10 to 0 is negative 8 plus 5. So that's our y value. We have an inflection point at 0, comma, negative 8 pi plus 5. Okay? And then lastly, we do the same thing with the 4. And let's see here. I guess I'll have to go down here to the bottom left. H of 4 means we take the accumulated area from negative 10 to 4 of f of t dt. Okay, so let's go back to shading. So I've already shaded the, from negative 10 to 0. If I keep shading, I'll get the other side of that. I'll get the other side of that isosceles triangle. But then we stop shading at 4. Notice I go below the x-axis again. So I get half of that next isosceles triangle, which is like that. Now, I think that was an identical, again, it was an identical isosceles triangle, so I know that half of that will be an area of 5 or a net area of negative 5. So let's see, if I add those up, if I sum those regions, the semicircle has a net area of negative 8 pi. The blue isosceles triangle has a net area of, we said, 10. And then the half isosceles triangle, so the right triangle that's below the x-axis, has a net area of 5. So we get a y value of negative 8 pi plus 5. Oh, so it's the same. It's the same value. I didn't realize that. Same value. Negative 8 pi plus 5. Okay. So we have found the inflection points. We have found the local extrema. We've found the intervals of increase and decrease, and we have found the intervals of concavity. Let's verify our answers. I guess that's the last thing to do. So I did pre-make this function because it takes some time. Basically, it's a piecewise function, so I have to type a bunch of stuff in. I've not verified our answers, though, so I am genuinely curious to see if these answers are correct or not. But here's what I want to stress to you. I kind of gave you a rough sketch of what the graph would look like when we first started the problem. But let's think about why this is the graph of h. Okay, so we're starting at negative 10. At negative 10, we haven't accumulated any area yet. Therefore, the y value of h is 0. You get negative 10 comma 0. But as soon as you start marching along the x-axis to the right, we start accumulating negative area. In other words, the function gets more negative because we're accumulating more negative area. And we keep accumulating negative, again, negative net area, negative signed area, until we get to negative 2. Because after negative 2, we start getting some net positive area because we move above the x-axis. So it makes sense that we have a little valley here at negative 2. And we start adding area, positive area, between negative 2 and positive 2. And then at positive 2, we start adding negative area again, so we start decreasing again. And we follow that pattern. Okay, so now what were our answers? Let's verify our answers. We said that we were decreasing from negative 10 to negative 2. Yep, we're definitely decreasing from negative 10 to negative 2, and then again from 2 to 6. So there's 2, and there's 6. Yes, we're decreasing over those intervals. That's indeed correct. Now we're increasing everywhere else. So that means we are increasing between negative 2 and positive 2, yeah. And we're also increasing from 6, that little valley down there, to where we stop, which is at 10. So yes, our increasing and decreasing behavior was correct. Now what about our extrema? Okay, we said we had a local minimum at negative 2, 8 pi. So I guess the question is 8 pi about, because Desmos rounds those irrational numbers. So let's see, is 8 pi about negative 25.13? Yeah. Negative 8 pi is about negative 25.133 if you round it. And then we also have, what, 6 comma 8 pi. Oh, why is it telling me 6 is undefined there? It's not undefined. Here, I'll manually put in the point. I'm not sure why. Oh, see, now you see why it took me a few minutes to type it all out. It takes a good bit of work to type that out. 6, I'm not sure why it's showing a hole there. We'll say negative 8 pi. We'll plug the hole. That's just Desmos being weird. All right, there we go. Okay, so we have these relative minimums at 2 comma negative 8 pi and at 6 comma negative 8 pi. And we said we had a local max at 2 comma negative 8 pi plus 10. So is negative 8 pi plus 10 equal to about 15.333? Yeah, it is. So we're good so far. And now let's talk about the concavity. Okay, now it's kind of hard to see concavity, so let's insert the inflection points. Okay, because that'll help us to see concavity easier. So we had an inflection point at 6 comma negative 4 pi. Oh, it's negative 6. I was about to say that's not a point on our graph. That looks much better. All right, got scared for a second. And then we had an inflection point 0 comma negative 8 pi plus 5. Okay, that's a point on the graph. Yep. Then our last inflection point was 4 comma negative 8 pi plus 5. Okay, yeah, those have the same y value. Okay, so let's look at that inflection point. So to the left of that inflection point, yeah, we can see the graph is bending downward, concave down, which matches up with our answer from negative 10 to negative 6, concave down. And then we had from what? From negative 6 to 0, so between those two inflection points, the graph is concave up, opening upward. Okay? And then you go from this inflection point 0 comma about negative 20, what was it? Negative 8 pi plus 5, and then to 4. So from 0 to 4, the graph is concave down, upside down parabola shape. And then afterwards, from 4 to 8, so from 4, oh, and I didn't have over here. Oh, yeah, no, that's just 6. Let me put 8. What is the y value at 8? Oh, we didn't have that. Okay, so I'll just do, let's see, 8, and, let's do this. X equal 8. I'll just cheat to find the y value real fast. X equals 8. So the y value is, oh, negative 7 pi. That's easy. So 8 comma 7 pi. Oh, negative 7 pi, rather. Now that's not an inflection point. That's where it changes from concave up to no concavity. So I just wanted to add that in there. So we said it's concave up from 4 to 8. And yeah, you can tell it's like an opening upward section of a parabola, so concave up. But then notice what happens at 8. We said from 8 to 10 there's no concavity. So from 8 till the end of the graph, no concavity. And look why that is. Because the graph turns linear. Whenever you have a linear graph, it has no concavity. So like f of x equals x or 2x. A linear function, a straight line has no concavity. That's why there's not an inflection point there, because there's no change from increasing, from concave to concave down or anything. It's just nothing. We change from concave up to no concavity, so that there's nothing special on the graph there. Okay, so all of our points checked out, all of our inflection points checked out, all of our extrema checked out, our increasing, decreasing behavior checked out, and that's cool. That's super cool. So I like this question. Okay, I like this question a lot because it really forces us to really wrap our heads around, like, okay, first of all, accumulation functions, and then how to take the derivative of an accumulation function, how to evaluate accumulation functions using a graph, what accumulation functions mean, and then also it gets all the stuff about derivatives. Derivatives being slope, and observing where a function is increasing and decreasing, because that's how we got the concavity behavior, because it turns out that h double prime is equal to f prime. Anyway, super interesting problem. I love that problem. That's why I included it here. I've seen that before here and there, and so I decided, hey, I like that problem so much, I'm going to add that to our course notes. So if you want me to help you, wrap your head around any of this, please let me know. If you want to see more of these examples, well, guess what? There's going to be some in your homework. So you'll see some in your homework very similar to this. And again, I think they're super cool. So, always reach out if you need any help. Never hesitate to reach out. Make sure you're putting in the time and effort every day to the tune of a couple hours, and you'll come out okay at the end of this class, which we're quickly approaching. Okay, so I'll catch you in the next video, and always make sure to reach out if you need help. I'll see you soon.